Hello everyone, I'm Christopher Livingston. I'm here today to present on my semester project for spring 2013, embedded graphics on the DE2-115. This is for Fresno State ECE 178 embedded systems over at the Lyles College of Engineering. I'd like to give special thanks to the instructor, Dr. Razy, for teaching an excellent course. So without further ado, on to the presentation. So as a quick overview, we'll go over the objectives, what exactly I set out to achieve with this project, some background behind the systems and software, and then we'll go into the actual process of development. Then we'll have a quick demonstration of the project in action. We have some video clips there. And then finally a conclusion, lessons learned, possible future plans and developments for this project. So objectives, simply put, graphics on an FPGA or field programmable gate array. Basically, this consists of two halves. There's software to draw the demonstration and then a hardware design to support that software. A lot of the particulars of the software, particularly with 3D rendering, those are coming in from Computer Science 172, computer graphics. I'm not going to go into that part in excessive detail here. This presentation is mainly focusing on the hardware aspects of the course. So some quick background on the hardware. Field Programmable Gate Array, better known as an FPGA. It's a digital hardware canvas. It's kind of like a big pile of Legos. You put them together to form different circuits, different digital logic designs. Basically, it consists of a number of logical elements and memory blocks. Now, these individual logic elements you can see in the lower right-hand corner are a set of lookup tables and logical functions programmed by an outside system. So it can be configured to act like a CPU, it can act like a digital signal processor, any number of things. In this particular project, it's configured as a computer system. We use intellectual property cores, or IP cores for short, mainly from Altera. We're using their soft CPU, the Nios 2, and then we're using memory controllers to access external memory, input-output ports, and a few other blocks to get our graphics pipeline up and running. So a bit of background on the graphics. We're projecting a 3D model, in the case of this project, a cube, to a 2D screen. There are a number of points in 3 space. However, we're trying to get them into 2 space. And there's a lot of linear algebra involved, matrix multiplication. You can actually see on the lower right-hand corner of the screen, there's a perspective transformation multiplying a set of homogeneous coordinates in 3 space, converting them into 2 space. This is very floating point intensive, so we had to add an additional floating point unit to the Nios 2. Normally it doesn't come with floating point instructions. Everything is wireframe as far as the drawing is concerned, so there's no texture mapping or anything like that. Altera's library has a Bresenham algorithm-based line drawing function for this program. And then for drawing individual frames, we're using the double buffering concept, where on the back side of a frame, the image is drawn and then the frame is flipped, so to speak. The pixel buffer then points to the new frame to refresh the picture very quickly. So for hardware equipment, we're using the Jurassic DE2-115. That's the circuit board pictured there. A VGA monitor. And then for cables, we have VGA cable to connect the DE2 to the monitor and a USB cable to connect the DE2 to the computer. At a bare minimum, that's the hardware required. Not a whole lot going on there. Software is a little more involved. We're using Altera's design suite, that is Qsys 2. That's their digital design software for just general purpose design. So if you're designing an IP core, anything like that, you'd be using Qsys 2. Also for compiling HDL designs, you would also use that. Next, we'll be using Qsys. Qsys is Altera's main integrator when it comes to IP cores. Put them together, make a system. For actual programming, we're using the Nios 2 Embedded Development Suite, which you can see that pictured on the right-hand side. It's basically Eclipse running plugins for C and C++ and Nios 2. So those of you who have programmed in Java before, it's pretty familiar. It's very similar. So for prototyping, I wrote prototype code to run on the system before I actually had the system running. Prototyping was done in C using SDL, Simple Direct Media Layer, using the Code Blocks Integrated Development Environment. So real quick overview, hardware-wise, I designed a system using the Nios 2F CPU. That's Altera's performance-oriented version of the Nios 2. It has an embedded cache, faster instruction fetch. Common features among the Nios 2, it's a RISC architecture based on MIPS, also very similar to ARM. There's an additional floating point unit added. For memory, main memory, there's a SDRAM controller to interface the DE2-115 board's 128 megabytes of SDRAM. And then video, the 2 megabytes of SRAM is used as a pixel buffer. Altera University program has an IP core that automatically configures the clocks using a phase-locked loop, or PLL. There's the 50 megahertz system clock that's derived from an onboard oscillator, and the 25 megahertz VGA clock. The whole thing runs on Altera's proprietary Avalon bus. All Qsys and older SOPC builder systems use the Avalon bus in this context. So for video, there is a pixel buffer, which is a DMA device, direct memory access device, that accesses the 2 megabytes of SRAM. Then there's a character buffer, which is a separate device used for overlaying text on the screen. It's actually very similar to old monochrome monitor text rendering capabilities. Then a dual clock, first in, first out buffer that translates the pixel stream coming out of the pixel buffer from a 50 megahertz clock to that 25 megahertz of VGA clock. Then the scatter gather DMA, direct memory access controller, that's used as a field controller to move graphics information from the SDRAM to the SRAM. Then miscellaneous I/O for switches and LEDs, and a JTAG UART. Now this part is used for debugging and any logging heading back to the Nios 2 EDS. So over an overview of the general system design, we used Altera's Qsys. There's a very clear graphical user interface, simple bus connections, everything is point and click for the most part. There's configuration of individual IP cores, and it automatically generates the hardware description language code, whether that's VHDL or Verilog, for Quartus 2 to compile. And it also, additionally, generates drivers for Altera's hardware abstraction layer to simplify programming in the Nios 2 EDS. So this is really the starting point for the system itself. You can see the general outline of the system on the right. I kind of crammed it in there so it's a little small, but at 1080p you should be able to see it. For IP core sources, mainly we used Altera's embedded cores and the Altera University program cores. These are mainly DE2-115 board-specific cores, such as the VGA controller, because there's a specific VGA chip on the board that controller is designed to interface. So a quick overview of the graphics path and pipeline. The Nios 2 CPU in the upper left-hand corner of the diagram you see on the right, it mainly interfaces the main memory, the video memory, the pixel buffer, and the character buffer. So it sends text to the character buffer, and for line drawing, it can directly interface the pixel buffer. It can also clear the pixel buffer, but that's very slow. So to fix that, I brought in a DMA controller, independent of the CPU, that transfers memory from the SDRAM to the SRAM. So it very quickly transfers from wherever in main memory, copies it to SRAM. And the pixel buffer, it's sent to a video resampler that adjusts the bit rate of the video from 16 bits at 640 by 480 to 10 bits per channel, so 30-bit RGB. And then the alpha blender combines both the drawn graphics, the background and the lines, and the text from the character buffer all into one contiguous signal. That's then sent to the VGA controller and then out the port to the monitor. Then for integration, after generating this system, it was brought into Altera's Qsys 2. You can see a block diagram of the system. That's actually the entire schematic for the system within Qsys 2. Very simple, just a lot of pins. Fortunately, there is a pin configuration file for the DE2-115. Importing it, automatically assigning pins as long as they're named properly was the biggest hurdle here. Then hardware compilation, which is much more time consuming than code compilation. Final result of the system actually used about 20% of the resources on the Cyclone 4 on the DE2 board. And then Qsys 2 also has an FPGA programmer, which we need to actually configure the hardware for the system. Software. For development of the software, we use the Nios 2 Embedded Development Suite. It's based on Eclipse, centered around Altera's hardware extraction layer, or HAL. For actually interfacing the hardware, we use JTAG, Joint Test Action Group debugging. On the actual hardware, there's application code was in Eclipse. There are two separate projects, one for application, the other for the board support package. The application is the part that's actually written. There's the 3D support code, so all the matrices, projections, vector math. Then I/O support subroutines, so for talking to the switches, LEDs on the board. And then the main subroutine, which is the root of the program. And the board support package, which is generated by Qsys and the Nios 2 EDS, it shouldn't be touched by the programmer. It can be referred to as a reference and it can be modified, but each generation it gets changed as it contains the drivers to actually run the hardware abstraction layer. Prototyping of the code for 3D rendering, it was prototyped on the PC using code blocks and simple direct media layer. So here in this video clip we have a quick viewing of the software prototype. It's the rotating cube with the perspective projection. Then there were challenges in development, namely with the DMA. That was the most time-consuming part. Originally, I used the Altera conventional DMA, which does one big transfer all at once. On paper, this looked like a good idea until I actually fired up the board. As you can see here on the slide, and I'll show a real quick clip of that, it distorted the video output of the signal. As a solution, it was changed over to Altera's scatter-gather DMA controller. And the main difference between the two is the scatter-gather does numerous small transfers. And it's easier to program many small transfers instead of one big transfer. Then we also had issues with the pixel buffer, mainly in coordinate formats. And there's an unresolved bug where the buffer seems to flip prematurely, despite the code telling it not to. Despite extensive debugging, I wasn't able to find the source of this glitch. You can actually see a little bit of it in the demonstration later in the video. So here's a quick clip of the DMA distortion. I'm switching the DMA on and off. So the part where the picture becomes all garbled is where the DMA is actually, well, where the conventional DMA was actually running. Fortunately, this was fixed. Here we have a demonstration of the program running on the DE2-115. Here I am switching on the board. You'll notice a quick little working blurb. And there is the cube. It looks like a square right now because of the camera projection. I'm going to go ahead and start the rotation switches. Momentarily, it'll switch to the red fill. There it is. Notice the cube is rotating much faster. This is because of the scatter-gather DMA controller managing the fill instead of the CPU. Then we've switched it to the perspective camera and we've changed the fill buffer to a gradient image. Still using the same DMA controller. Frame rate is roughly the same. There we go. We switched back to solid fill buffer. And then we switched back to the orthographic camera. A little bit of back and forth there. And then notice now we're back on the CPU fill. Again, it's much slower because the CPU is manually doing everything. Back to the DMA for more contrast. back to the CPU again, and then back to the gradient fill buffer. Now, it's worth noting that, again, these fill buffers are stored in main memory. They're just being copied over to video memory using the DMA controller. Switched rotation axes. Rotation is disabled, enabling it again. Kind of get a stationary image. Since it's continually pulling the switches, everything is being updated in real time. And that's the demonstration. So wrapping things up, in conclusion, overall, the project really was a success. There was a working demo, and I managed to combine concepts from both ECE 178 and Computer Science 172. So taking computer graphics, rendering them in embedded systems. Some lessons learned. The project scope was initially very vast. Now, there was an initial design for vector acceleration. The progress was made there. However, there just wasn't enough time in the semester to complete it. So that will be potentially used for another project. Troubleshooting was definitely an issue. The DMA fill buffer problem occupied a good solid couple of days. For future plans for this project, more acceleration. So there's already a vector processing unit in the works, and then possibly even expanding that using various DMA techniques into a simple GPU. Then for software plans, obviously this is just wireframe, so there's a lot more that can be done here, such as texture mapping, shading, taking better advantage of the hardware. There's a lot more that can be optimized. So in review, I went over the objectives of the project, the background for both the hardware, software, and the graphics portions, the development process itself, demonstration of the project, and then a conclusion going over the various aspects of the project, lessons learned, and whatnot. That concludes my briefing. If you have any questions, there's my email. So, all right, well, thank you for watching.